talking about complex numbers. So the first thing we have to talk about with complex numbers, right, is that I is going to be popping up quite a bit. This is the square root of -1. Any number that has this I in it, we think of as an imaginary number. It's kind of the name that's stuck with them over the years. I want to emphasize they are not imaginary. They are no more imaginary than negative numbers are. They are used in lots and lots and lots of areas of math and science, even in showing up in fundamental equations, in quantum mechanics that kind of govern what reality is like at a small scale. So not imaginary. So what does the complex plane look like? So we're all familiar with the real number line, right? Over here, we have numbers on it. 1, 2, 3, 4, 5, 6, if we kept going, and then we have the negative numbers to the left of 0. The complex plane is made up of this real number line and then also the imaginary number line, which is perpendicular to it. Okay, and this has I, 2i, 3i, etc. And so when you are in the complex plane and you multiply something by I, right? Complex numbers, like let's look at what happens if I start with 1 and I multiply by I. That's going to take me over here like this, right? If I multiply 1 by I get I. If I multiply I by I, well, then I get -1 because I have the square root of -1 squared is -1. If I multiply by I again, I'm going to get over to -I. If I multiply by I one more time, we get back to 1. So multiplication by I is actually just rotation by pi over 2 in the complex plane. Okay. Good. So complex numbers more generally, right? These are any number of the form z equals a plus bi. A and b are real, and I is obviously imaginary. If we take this complex number and we're talking about the real part of the complex number, that's what this means here, the RE kind of z equals a. This is saying the real part of z is a. Similarly, the imaginary part of z is b here. Okay, so let's look at how we do some operations with complex numbers, like addition and multiplication. Suppose we have two complex numbers, z1 is a1 plus b1i, and z2 is a2 plus b2i. We can add these, z1 plus z2, in the same way that you would add, like, two polynomials together, where one of them has a constant and then like an x, right? You add this stuff that's similar. You add the real parts, you add the imaginary parts. So I have a1 plus a2. I'm just gonna put in parentheses. The parentheses don't do anything, right? They just kind of indicate that, oh look, this is all real. And over here I'm gonna do b1 plus b2 times I, so you can see I have an imaginary part made up of b1 plus b2 and a real part made up of a1 a2. So pretty straightforward to add complex numbers. You just add the corresponding parts. Multiplication, we're going to do z1 times z2. You FOIL. So I would have a1 plus b1i times a2 plus b2i. And we have to FOIL this out. So this is going to be a1 a2. Then we're going to have plus a2 b1i. And then we're going to have plus a1 b2i. And we're going to get plus b1 b2i squared, right? I squared is -1. So this is going to turn into z1, z2 will be, I have a1, a2 over here. And then this is going to be minus b1, b2. Those are going to be the real bits, right? So I'm going to have a1, a2 minus b1, b2. And then I'm going to have plus the imaginary bits. So I'll have a1, b2 plus a2, b1 all times I. Okay. So this is less nice than addition. Multiplication is like kind of, we don't want to memorize this, right? This is like kind of a pain to memorize, and it'd be also a pain to have to FOIL it out every time. So we're going to look at an easier way to do some of these operations kind of in a different form. But this is, it kind of shows you can do multiplication and addition in this representation of complex numbers. Let's look at another kind of operation or quantity, the complex conjugate. Okay, so if z is a plus bi, then the complex conjugate of z, which will often be notated as z star, you might also see z bar as well, is equal to a minus bi. So anytime you have a complex number and you want to take its complex conjugate, all you do is you take the imaginary part and you put a negative sign in front of it. Okay, so if it's negative, it turns positive. If it's positive, it turns negative. Okay, you might ask, what is the point? Why do I want to just put negative signs and stuff, right? So let's look. If I have a number here in the complex plane, if I have a number that's just like right on the real axis, we have this idea of an absolute value, right? Where I can say how far away from the origin is this number, and then I can say, okay, it's it's that far, and whether it's positive or negative, it always turns out to be positive. The way we typically do that, right, is we say, okay, this is going to be, you might maybe I'm unfamiliar with this, but the absolute value of a number, will say c, some constant. The absolute value of some constant c, we can define this as the square root of c squared, right? So I would like to have some kind of absolute value quantity in the complex plane. I'd like to know what this distance is, right? And if I try to apply the same definition of absolute value to z, I get the square root of z squared, which is the square root of, I have a plus bi, and if I do this out, I'm going to get a squared plus 2abi, and then minus b squared. This is bad, right? This is, if I take the square root here, this is very much not what we were hoping for, because I can look at this, right? This is just a right triangle. I can look at this and say, well, if I have a right angle here, I know the real part has a length of a, the imaginary part has a length of b. This should be just a squared plus b squared, right? Square rooted. That's what that should be. And instead, I have something that very much does not look like that. So we can actually use the complex conjugate to obtain this idea of an absolute value. So absolute value, it doesn't correspond perfectly to complex numbers, as you can see. So instead, we call it the modulus. We say the modulus of a complex number. So same kind of notation. The modulus of z, we say, is the square root of z times the complex conjugate of z. So z times z star. So if we do that, what happens? Right? We know what we should expect to get. I have a plus bi times a minus bi. Right? This is a difference of squares. So now I get the square root of a squared, and then minus b squared, I squared. I squared is -1, so that turns into plus b squared, right? So this recovers the actual quantity that we're looking for. This kind of, I can't quite say it's a distance, but this idea of how far away it is from the origin, okay? So that's where complex conjugates are helpful, is this idea of the modulus, which is kind of a complex version of the absolute value. All right. Good. So, complex numbers, you can do stuff like them in Cartesian, as you saw, but we can also do stuff with them in polar. And doing it in polar will often make some of the operations we were just looking at much easier than they were in Cartesian. So suppose we have a number, and this, if you watched my video on polar coordinates, this derivation is, essentially identical to that, right? Except now I have an imaginary axis and I have a real axis. So this is a complex number z. I can write this as a plus bi, right? Because I can say, this, b a. But I could also say, well, this makes an angle of theta with the real axis, and it has a modulus of r away from the origin. And then I can say, well, maybe I could write this in some kind of polar form, right? I could say a is going to be equal to r cosine theta, and b is equal to r sine theta. If I, kind of wanted to go the other way, I could do the same thing that I did in polar. I could say that r is equal to the square root of a squared plus b squared, right? You can see that geometrically, and that's also the idea of the modulus we just talked about. And then theta is the arctan of b over a. So we're going to take these, and we're going to take this, plug it into this, and get a new form of a complex number, right? So I have z equals a plus bi, and I'm going to plug in this new polar stuff into here. So this is going to turn into r cosine theta plus r sine of theta, and this one is being multiplied by I, right? So I'm going to factor out the r here. So I'm going to write this as r times cos theta plus I sine theta. And this is going to pop up a lot, so we're going to give it its own notation. We're going to say that this is r cis of theta, okay, r cis theta. Now, as you go on, and even as we're going through and doing this stuff, pay attention to the properties of cis theta. Because right now we're calling it cis theta because we haven't really done complex exponentials, but e to the I theta is equal to cosine theta plus I sine theta. This is something that you can find lots of proofs for. We might even prove it later on in the year. But for now, we're going to do stuff without complex exponentials. And so this, we would expect cis theta to have all the same properties that e to the I theta does, basically. So just pay attention to that, but we're going to stick with r cis theta, that kind of form there. Okay. So now that we have that, let's try to see if we can convert back and forth between the forms, right? Let's do some conversions. So let's say we want to convert z equals the square root of 3 minus I to polar form. Okay. So if I want to do that, I can get r, right? R is going to be the square root of root 3 squared, and then plus -1 squared. Note that as we do this, right, we're not including the I. We're doing the imaginary part, which is just the coefficient of the I. And this is going to give us 2. So we have r is 2. And then I can say, what is the arctan of b over a? So -1 over root 3. This is going to be equal to 11 pi over 6. You could also do it with, you could do like an inverse cosine of root 3 over 2. And things. You could do any kind of variant of this, right? Just like you could with polar. Just make sure you end up in the right quadrant, right? This point is located in quadrant 4, right? Root 3, -1 is down, so we're in quadrant 4. So we need to make sure that whatever we get is also going to be in quadrant 4. So if you get something like, I don't know, pi over 6, let's say you did an inverse tangent, you get pi over 6. Make sure that you move that into the correct quadrant by saying, well, I know it's supposed to be in quadrant 4, so I'll do 2 pi minus pi over 6 to get 11 pi over 6. Okay, and once you have this, then you can say that z is equal to 2 cis 11 pi over 6. And remember what this means, right? This is not like a new trig function. It really means 2 times cosine 11 pi over 6 plus I sine 11 pi over 6. It's just a more compact way of writing it. Okay. If you want to go the other way, it's really easy to do, right? So let's say this time instead we want to convert z equals 5 cis 144 degrees to Cartesian. And I'm using this Cartesian term kind of loosely. I just mean, a plus bi form rectangular coordinates. So when I do this, here we just expand this and say, well, this is just 5 times cosine of 144 degrees plus I sine of 144 degrees. And you literally just put this in a calculator, right? And, you do cosine of 144. Make sure you multiply it by 5. Make sure you distribute the 5 to both of these, not just the cosine. Common thing people do is because they get so caught up in doing this part, they only distribute the 5 to the cosine and not also to the sine. Make sure you do both. So if you do that, you should get -4.04508 plus 2.93i, about. All right. So you can go back and forth with relative ease, just once you have the conversions. All right. So we're going to look at some properties of complex numbers in polar form. Properties in polar. So first, we're going to look at multiplication. We did multiplication with Cartesian, the Cartesian form, and multiplication in polar is going to be a lot nicer. So we're going to take 2 complex numbers. Z1 we're going to say is R1 cis theta 1, and Z2 is R2 cis theta 2. And I'd like to multiply these together. So I'd like to do Z1, Z2. Now, sure, you could convert these to polar, right? Or not polar, Cartesian, and then you could multiply them in Cartesian by foiling everything out. That is going to be a huge pain and very unpleasant. So let's see if we can find a nice, easy way to do it. So this is going to be R1, R2 times, and I'm going to expand these out to more capably work with them. So it's going to be cosine of theta 1 plus I sine of theta 1 times cosine theta 2 plus I sine theta 2. And then I can FOIL this, right? So this is going to give me R1, R2 times, and we're going to have cosine theta 1, cosine theta 2, and then we're going to have plus cosine theta 1, sine theta 2, times I, plus cosine theta 2, sine theta 1, times I, and then plus I squared sine theta 1, sine theta 2, right? So I squared is going to be negative 1, so we're going to get minus sine theta 1, sine theta 2. So then, I mean, this looks like a disaster, right? But the discerning among you might notice that if I look at the real part, right, which is this, let's move them into like the real part and the imaginary part, right? So this is R1, R2 times, and I'm going to write this as we'll do cos theta 1, cos theta 2 minus sine theta 1, sine theta 2. And then we'll do plus I times cos theta 1, sine theta 2, plus cos theta 2, sine theta 1. And now, written like this, maybe it's a little bit easier to see, but these are both trig identities, right? Cosine theta 1, cosine theta 2, minus sine theta 1, sine theta 2. This is just equal to cosine of theta 1 plus theta 2. Similarly, over here, this is just equal to I sine of theta 1 plus theta 2, which means I can write this as R1, R2 times cis theta 1 plus theta 2. So the derivation to get here is, more involved than multiplying two numbers in Cartesian, but the result is much, much nicer, right? If I want to multiply two numbers in polar, you multiply the moduli and you just sum the angles. And this also suggests something interesting, which is that multiplication in polar, right, actually involves a rotation and not just a change in length, right, or distance from the origin. This was suggested because multiplication by I rotates us by pi over 2. So if we multiply by another complex number, it should probably rotate us by something else, right? And it does. So that's multiplication in polar. Okay, let's go to we'd like to do quotients, but before we can do quotients, we're going to do reciprocals. So we're going to take a number z equals r cis theta, and we want to reciprocate it. So I want to do 1 over z and figure out what that is. So we're going to have 1 over r cis theta. I do not need a 1 here. We'll just keep this as theta. So as always, I'm going to expand this out to be more able to work with it. So this is cosine theta plus I sine theta. And ideally we'd get this into some form that's going to involve a cis of something, right? And so I'd like to get this denominator bit out of here and kind of into the numerator. So we're going to multiply by the complex conjugate. So I'm going to multiply this by cosine theta minus I sine theta over cosine theta minus I sine theta. And when I do that, I get cosine theta minus I sine theta divided by r times cosine squared, and then minus I squared sine squared, but I squared is negative 1, so it turns into plus sine squared theta, right? So then my new denominator, cosine squared plus sine squared, is just equal to 1, so I get 1 over z is equal to 1 over r times cosine theta minus I sine theta. And then here, it's kind of annoying because cis theta specifically has a plus sign. We have a minus sign. So I need to turn this into a plus sign somehow if I want to write this in cis form. So what I'm going to do is I'm going to say, well, I know that negative sine of theta is just the same thing as positive sine of negative theta. So I'm going to write this as plus I sine negative theta. But if I do that, I need my cosine to have the same argument, right? If I'm doing cis theta, I can't have sine and cosine of different arguments. So that means cosine needs to have a negative theta inside. And luckily, cosine is an even function. So I can just add a negative inside of the cosine, and it doesn't change anything. I can just write this as cosine of negative theta, right? And these two statements are equivalent, which means that now I get to say that 1 over z is equal to 1 over r times cosine, times cis of theta, negative theta. There you go. So that's a reciprocal of a complex number. And now that we have reciprocals, we can do quotients. Right? We can divide them. So let's look at quotients. So to do quotients, we're going to do, again, we'll take two numbers, z1 and z2. We want to divide them. And this is going to be, I'm going to write this as z1 times 1 over z2. And then I'll expand it. Because then I know z1 is just r1 cis theta 1. z2, right, 1 over z2, I should say, is what we just found from the reciprocal, right? So I can write this as 1 over r2 times cis of negative theta 2. So then z1 over z2 is equal to r1 over r2 times cis theta 1 cis negative theta 2. And then I can go back to my rule for multiplication and just say, oh, well, if I'm multiplying two things, I just add the angles. So this turns into r1 over r2 times cis of theta 1 minus theta 2. And that's our quotient rule for complex numbers. Okay. So those are all the big kind of base level intro properties for complex numbers. In the next video, we're going to look at how to do powers and roots. And we're separating those out because that is kind of its own thing. It has its own kind of interesting theory around it. So I want to devote a video to talk about that. Great. Thanks for watching.